So for this week, I decided to do number 29 from chapter 10. Number 29 revolves around a situation where the American Medical Association needs to book a large number of rooms for their upcoming conference. That's in 6 months. In the current state, they can rent a large quantity of rooms for $150 a night. And then at the time of the conference, if there are any extra guests that rooms were not booked for, they can book rooms at that time for $250 a night. So the problem lies that the American Medical Association wants to book these rooms at the cheapest cost to them. So the information that we're working with here in part A of this problem are those two costs: the upfront room cost of $150 that can be booked now, or $250 that can be booked at the time of the conference. In part A, we're looking at a demand distribution that is normal, and they have determined that the mean of attendees of the convention will be 5,000 with a standard deviation of 1,000. So what we want to do here is determine how many rooms the American Medical Association should book now at the current time in order to best utilize their costs. So we have a decision variable here with our room quantity of 4,000. We're going to run several iterations. So we have a sim table laid out here. We're doing 10 simulations from 4,000 to 4,900 in increments of 100. In the simulation, we're going to look at the demand. That's going to be our randomly generated variable. It's going to be revolving around that 5,000 mean with a standard deviation of 1,000. And then we have two costs associated with the total cost that the American Medical Association will pay. So first of all, they have their upfront room cost. So this will be the room quantity times the upfront room cost. So the current state, we're room quantity of 4,000. We will be paying $600,000 in upfront room costs. And in the situation that's currently laid out here, we have a demand of 5,000. So we have an excess of 1,000 rooms that need to be accounted for at the time of the conference. So that difference between the demand and how many we actually ordered of 1,000 rooms will be multiplied by $250, that cost of getting the room at the time of the convention. And in the situation that demand is lower than the room quantity that's ordered by the American Medical Association 6 months in advance, this extra room cost will be $0. And our total cost for the entire convention is this upfront room cost plus the extra room cost, giving us our total cost. And this is going to be our output variable that we are looking at here. So in order to determine the best situation for American Medical Association in terms of how many rooms they should rent up front, we are going to run a simulation. I've already set it up here. We're going to do 1,000 iterations times these 10 simulations that I have laid out. As I mentioned before, we have a demand distribution that's normal for this part of the problem. So we have this laid out here with a normal distribution of these two components. And once we run the simulation, which was very quick, we come upon a mean for each of these simulations. This is the average price, or the average total cost for the AMA, based on how many rooms they ordered up front. So what we want to see here is the lowest total cost, and that will help us determine how many rooms we should order now. And as we can see here, we start out very high at 870,000 when we're only booking 4,000 rooms, and it's continually decreasing, right? Until we get to simulation 8 here, which is equating to 4,700 rooms booked, and that has an average total cost of $846,000 and some change. A little bit cheaper than our simulation 9, which is the equivalent of 4,800 rooms. So based on the simulation and the randomly generated variables, we've determined that simulation 8 of booking 4,700 rooms will be the cheapest. Now, though it is the cheapest on average, there is still the standard variation that we will have to look at. So in the case of booking 4,000 rooms, it may be the most expensive on average, but the standard deviation is much higher. So there's greater potential for it to be lower, but there's also that greater potential for it to be higher. And that standard deviation continues to decrease as we go down the line because we have less deviation possible because of the fact that there won't be as many extra rooms that will need to be booked. So that's part A of this problem. Part B of the problem is very similar. The only thing that changes here is our distribution model. So in the first distribution, we had a normal distribution, and I need to change this here. This is a triangular distribution model where we have the minimum rooms to be booked is 2,000, the most likely being 5,000, with the max being 7,000. And we're going to run almost the exact same simulation here. We have the same 10 simulation points ranging from 4,000 to 4,900. We're going to have the same equations here, the upfront room cost, the extra room cost, and the total cost. The only thing that will change is our demand output, or demand input rather, and that's going to look at these three distribution points in the triangular distribution. So we're going to do the same thing, run 1,000 iterations times 10 simulations, and we're going to get the same kind of outputs here, where we're looking at mean, standard deviation, and percentiles. So if we're looking at mean, we will see here that once again our highest average cost, or one of our highest average costs here, is at that 4,000 rooms booked, and is going to continually decrease until we hit simulation 5, which is our simulation of booking 4,400 rooms. This has the lowest average cost for the American Medical Association. And once again, we have the highest standard deviation at our lowest number of rooms booked, and that continually decreases, once again because of the fact that we won't have to book as many potential extra rooms at the time of the convention. So we do get a different result here. In our first simulation, we decided that they should book 4,700 rooms, which is our 8th simulation. And in our second part, we determined that we should book 4,400 rooms, and that would be the cheapest. And we do get a difference here, and it's all due to the fact that we have different distribution models. They give us a different determination of what the average will be and how that demand moves about randomly throughout that distribution model. So in our recommendation, with the normal distribution, we would book 4,700 rooms. In our triangular distribution, we are going to book 4,400 rooms in advance.